Okay, sixth grade. So it has, I'm starting through the sixth grade videos. I'm able to go faster now. Figured out some things that were really slowing me down. So Mr. Bailey helped me to solve some technical issues. So we're going to try to go through, get some videos out to you guys. This is session 1, number 17, and we'll go through the problems and then we'll also just discuss them a little bit so that we can review some of the things that we've gone through. Okay, which number has an absolute value greater than 5? So that term absolute value, what does that mean? The term absolute value simply means how far a number is from what? Do you remember? All it means is how far it is from 0. So if we come out here and go 1, 2, 3, 4, 5, 6, if we have the number 6, the number 5, back here we have 1, 2, 3, 4, 5, 6. So negative 6, negative 5, negative 4, negative 3, negative 2. I won't put all of them in there. Remember, on a number line, as you move to the right, numbers get further from 0 and they get larger. Okay? More positive. As you move to the left, they become more negative. They get smaller. So on a number line, moving to the right, no matter where, anytime you move to the right, the numbers are getting larger. So here's negative 6. As you move, it gets larger. Even though it's still negative, it's closer to 0, getting larger. And then here, getting larger, it's positive and away. Okay, so what's the absolute value of negative 6? They use those symbols. It just means how many spaces from 0. Well, negative 6 is, how many spaces from 0? It is 1, 2, 3, 4, 5, 6 units from 0. So the answer is 6. The absolute value of negative 5, oops, I'll just leave it on that, is only 5 spaces from 0. So it's not going to be quite as far. 5 spaces, 1, 2, 3, 4, 5. So we'll put that one in red over here. The absolute value of 5 is 5. And then the absolute value of 5, not 15, I want it to look like 15, is also 5. So if we come out to here, that's also, whoops, 5 spaces. 1, 2, 3, 4, 5 spaces. Okay? Which number has an absolute value greater than 5? So greater than, not equal to, it's going to be letter A. Nice. Let's look at the next one. Okay, let's look at 26. Let's look at 26 here. We're going to highlight some things in the question here, see if this will work. So a baker made 9 cakes using 3 bags of flour. Okay, so we're going to think about that. Yeah, that's too much. That's too much, right? Let's see if we can go back on that. We don't want to get all of that. Okay, and back. Tricky highlighter. So a bakery made 9 cakes using 3 bags of flour. The bakery uses the same relationship, so that's giving us an idea that this is probably going to be a ratio problem, because our ratio is about a relationship between two things. Same relationship between cakes made and flour. Which table of values, okay, shows the relationship between the number of cakes the bakery makes to the number of bags of flour? So basically we're looking for which table shows this relationship. Okay, so let's take a look at that, see if we can figure that out. So first of all, from the problem, I noticed that it's 9 cakes. 9 cakes, okay. Or you could say, yeah, for every 9 cakes, there are 3 bags of flour. So I'll put 3 bags. Or I can write it like this, 9 cakes to 3 bags. I'm probably going to put a little C over here for cake and bags. Okay, so what does that mean? So let's kind of explore that a little bit. If I actually were to draw that, if I had 9 cakes, it might look like 1, 2, 3, 4, 5, 6, 7, 8, 9. And if I had 3 bags of flour, maybe I'll use this color for flour. I might have 1, 2, 3 bags of flour. So that's kind of what this means. 9 cakes, there's my 9 cakes for 3 bags. This is supposed to be a B right here. Doesn't look like a B very well. 3 bags. There we go. So one of the things you want to know is, well, so how many, how many cakes can you make with just 1 bag. That's that unit, that unit ratio for just 1, okay? And if you look at our drawing here, it's really easy to see, well, one bag, I can make 3 cakes. 3 cakes with 1 bag. So then this is equivalent to, okay, 3 cakes for 1 bag. You can see this with a picture. You can always draw a picture, okay? It's a great way to visualize, something. You always want to make sure that you, whatever math you're doing, you can see it in your head what's going on in real life. And then you can also, because of your knowledge of fractions, we can treat this. It's a ratio, but we can also say, well, we have 9 cakes for every 3 of these. So you can actually do some division here. 9 divided by 3. Well, that means I have 3 cakes to 1 bag of flour. So your knowledge of fractions will help you. Equivalent fractions and equivalent ratios, very helpful. All right, well, let's go check it out. So this one here, we can see this one has a 3. Ooh, looks promising, a 3 and a 9. But this one says 3 cakes to 9 bags. We're not looking for that. We're looking for 9 to 3. This one looks good. It's got 9 cakes to 3. So we're going to put a question mark. That might be it right there. Let's just see what else we have. Let's see if we can make it easy. Oh, this one's also 9 to 3. So that one's a question mark. That one might be. This one is 3 to 9. 3 cakes to 9. So that's out. So now we're down to these two. So let's see. We also know that the value of this ratio is 3 to 1. So we've, in its simplest form here, 3 cakes to 1 bag. So this one says, this one in fact says, when we look for 1 bag, we look along here for 1 bag, it says 7 cakes to 1 bag. So we're like, whoa, that just doesn't look right at all. And in fact, if you look at this table here, it mathematically really is not making sense. So it's not even a correct value, a correct ratio table. It doesn't have the same relationship. So look, when you go from 7 cakes to 1 more cake, you go from 1 bag of flour to 2 bags. So in other words, for the first 7 cakes, you use 1 bag of flour. Then for this next cake, apparently they used a whole bag of flour. So either it's like a huge cake or it's going to be pretty dry and crumbly. So that does not look good at all, okay? It does not look good. So this, even though this has the ratio we're looking for, this table, the table does not show the relationship. This table does not show the relationship of basically 9 to 3 or 3 to 1. It's really 3 to 1 is the relationship. Okay? And this table does, in fact. So take a look at this. There's 3 to 1 right there. 6 cakes to 2 bags of flour. 6 cakes to 2 bags of flour is the same thing as 3 to 1. Okay? So this would be our correct answer. All right, let's keep going. Okay, this is a really good problem. This is a review of some concepts that you actually learned in 5th grade. So it says the volume of any cube with a side length s. So the side length is s, okay? The volume can be determined by using a formula, and you've talked about formula for triangles this year, is volume equals side to the power of 3. In other words, if you have a cube like this, and a cube means it has a height and a length and a width, and they're all the same. They're all the same. And volume is length times width times the height. That tells us volume. Remember, area would just be this bottom part right here, and that would just be length times width. So it's just the bottom. Whoops, maybe it's not gonna. See if I can get this marker to work. See if that'll go. No. Nope. We'll just try a different color. So the area would just be like saying, down here length times width, just this flat part. That's an example of area. But now we're talking about the whole thing filling up all the space. That's volume. So let's take a look at that. And volume is length times width times height, okay? But any cube, okay, if it's a cube, automatically that shape tells us the length, the width, and the height are the same. So you can write this formula. And remember, basically math. They're always looking for some kind of a shortcut. So instead of writing length times width times height, if they're all the same size, they're all the same. In other words, we could say, we'll use a variable, say, well, the length of this is S, the length is S, and the width is S, okay? All right. Or I could take this off, make it maybe not so confusing. Just say that all of those sides are S because it's a cube. So then we could write the formula as side to the power of 3, okay? It's just a short way of saying, because all these literally would be S, because I could write it like this. Volume equals the length is S times the width is S times the height is S. So instead of just writing it like that, S to the power of 3. Okay, so let's go to the question. What is the volume in cubic centimeters? Don't let that, throw you for a loop. That just, when you have area, you use square units. Volume is just using cubes, so we have cubic units. What's the volume in a cubic centimeters of a cube with a side length 2.3 centimeters? So in other words, instead of S, they're going to give us, they're saying this is 2.3. Okay, the length is, of course, going to be the same. That's going to be 2.3. And finally, the height, because it's a cube again, is, you guessed it, 2.3 centimeters. Okay, so now we just use this formula. We're going to multiply all these together. So I can come over here and I can say, okay, well, in other words, volume, if I use this formula here, so volume equals S to the power of 3. And all you do with the formula is just plug in values. Okay, it's just like a recipe, for example. I know what S is. It's 2.3 centimeters. And this is going to be to the power of 3. All right. Which means I'm going to have 2.3 times 2 3/10 times 2 3/10. Now, here's where you want to use some good test-taking strategies. Because look at this. You can estimate. So you can actually estimate, and you can get rid of some answers. Watch. You can estimate. This is about 2. So 2 3/10 is about 2, we're going to say. So what do you think 2, and I'll use the dot this time, times 2 equals? Well, 2 times 2 is 4, times 2 is 8. So notice we actually rounded down a little bit. So we didn't even include this 3/10. So our answer has to be more than 8. Wouldn't you agree? So there's that 3/10, right? So I said that's about equal to 2. So I rounded down. So then I multiplied 3 times 2 times 2 times 2. So our answer has to be more than 8. So automatically, it can't be this and it can't be that. Okay? Can't be. And you could kind of take a look at this actually and say, well, you know what if I just multiplied the 2 and the 2 and the 2, So, what if I did the 3/10? So let's go back. We're kind of not sure, and it's probably best right now to go ahead and do the actual answer. So let's do that. But at least we got rid of a couple of them. All right, so we've got 2 3/10 times 2 3/10. So we're going to have to multiply that. And we're going to have decimals here. And decimals simply means when we multiply, we don't have to really pay any attention to those, because kind of what we can say is when we're done, we'll take care of those decimals. So in reality, what you're doing is you're just treating it like this is, well, here, I'll show you in a second. Here we go. 3 times 3 is 9. 3 times 2 is 6, right? Now let's move over. Let's move over to the next place value. And we'll multiply by 2 times 3 is 6. 2 times 2 is 4. Okay? So you add all this together. 9. Make sure I got that right. 9, 2 times 3 is 6. 0, 6, 2 times 6 is 4. 9, 2, 1, 5. So right now I've got 9, 2, and I've got 5. And then I have to put my decimal over. And what's happening here is, it's really interesting. This is tenths. This is the tenths place, and that's the tenths. So I could really write that decimal like this. This is what's happening. You don't have to do this, but it's kind of interesting. So really what you're saying is 1/10 times 1/10 equals 1/100th. And that's why the decimal has to move over to the, so that there are values in the hundredths place. So it moved over 2 spots, we say. But again, the reason is there's a math reason. You don't just move stuff just because you're like, hey, let's just move stuff around. So there's a math reason behind that. Okay, now, ooh, this looks good. Wait a minute. Did we make a mistake? No. Remember, so we have to do 2 3/10 times 2 3/10, and we have to do it again. Okay, so let me clean this up and we'll finish up. We'll finish up our multiplication here. Okay, let's see if it gives me the same color. So now I have 5 and 29/100 times 2 3/10. And you're going to say, well, you know, I didn't line those decimals up, did I? Well, I don't have to, because when I'm all done, I'm kind of, you know, I'm gonna count the number of decimals, the number of digits behind the decimal, and use that. But you know what? I'm not even sure I have to finish this problem, because look at this. I have these two things to multiply. I can save some time here. This is about 5, and that's about 2. 5 times 2 is 10. It can't be this one. It cannot be that. That's why we multiplied it. So really, I can move on. I've got enough to show here, but let's finish it. Let's just go ahead and do that. So 3 times 9, 27. Okay, and 3 times 2 is 6, and then we have 8. 3 times 5 is 15. I'm going to cross this off, and I'm going to come back. Okay, I'm done multiplying by this in this place value. So now I'm going to go here. 2 times 9, 18. I'll carry 1. That's why I crossed that one off earlier. 2 times 2 is 4, 5. And 2 times 5 is 10. Okay, you can go back and look at that. Now I'm going to go 7, 16, 10, 11, 12, and 1. And now I say, you know, technically this is kind of interesting. Now I'll do it one more time. I really think it's kind of cool. Oh, I can't go off the screen there. I'll come down here, okay? I'll erase this and show you too, because that's pretty neat. I want you to know why you're moving the decimal over, okay? The shortcut, you don't even have to do all this, but it's just fun. So hold on a second here, hold on. Okay, so this number has decimals in the hundredths. That decimal has digits up to the hundredths place. Okay, this one has decimals up to the tenths place. What is 1/100th times 1/10? What's 100 times 10? 1,000. So I have to have, when I come back to this number, I have to have that decimal so that I have digits in the thousandths place. And that's why, that's why I have to have the decimal right here. Short way to do it is to say, hey, I have 1, 2, 3 numbers behind the decimal. I'm just going to move it over these 3 spots. Okay, and there's our final answer. Ta-da! All right, you're a genius. Let's keep going. Okay. It's a pretty cool problem. This is a common one, actually. Okay, here's 28. Mr. Tola has a piece of wood that is 8 1/4 feet in length. 8 1/4 feet. Okay, 8 1/4 feet. He wants to cut it into pieces that are 3/4 of a foot in length. So that's very common. A lot of times, you know, when you're doing a job around your house and you need small pieces of wood for all kinds of, you know, you always need small pieces when you're framing or propping stuff up. So this is like, he has 8 1/4 foot board. How many of these? And you should be circling and underlining and highlighting, okay? The question is what guides us. How many 3/4 pieces of wood can Mr. Tola make? How many 3/4 pieces? So let's just do some thinking about this, because first of all, he's got a board, and his board is 8 1/4 feet, right? So let's see, he's got, let's divide this up. He's got, I just divided it up really quickly into 1, 2, 3, 4, 5, 6, 7, 8, and then he's got like a quarter, a little bit more. Okay, so if you always draw a picture, and just to visualize, so there's 1 foot, we can actually see there's 1 foot. So let's see if we can get rid of some answers. So can he get 7? Okay, is he only going to get 7 3/4 foot pieces? Well, you could say, wait a minute. 3/4, that's less than a foot, and he's already got 8. He could get 8 1-foot boards, so that can't be right. Does that make sense? He can already get 8, so he's not going to just get 7. And here again, this one says, look, if you were to cut it, of course I just drew where I just marked off, on the board. We haven't even cut it yet, but if you were to, this would be a 1 foot board, another 1 foot. He'd have 8 of those. So this can't be it. Okay? And I'm suspicious about this one here. I don't think so. I'm thinking this one. This one looks pretty good right here. I'll put a star next to that. Okay, so what do we have? A lot of ways that we could do this. A lot of ways. But basically, you're saying how many sections can we find that are just 3/4? So if we were to draw that, how many 3/4 sections? So 3/4 would be like this. Okay, it's going to be small. So we're asking how many groups of 3/4 can we find in here? That sounds like division. So basically, you're saying I have 8 and 1/4, and I want to find out how many 3/4 boards can I get in there. All right, how many 3/4 boards? Well, you could, there's a couple things you could do before you even do division. You could say, okay, can I get 9? Well, what's 9 times 3/4? How much is that? There's a lot of ways to do this. That's why math is so fun, because you can come at this thing from all different directions here. So 9 times 3, that's going to be 27 quarters, 27 fourths, which is equal to, okay, so that's an improper fraction. So let's find out, if he had 9 3/4 boards, is that going to equal, we want to find out, is it 9? Does it take 9 to get all the way, to the end, or can we do more? So 27 fourths. So think about what that is. So 27, well, let's see. 27 divided by 4. 27 divided by 4. So 4 into 27, that's 6 times 4 is 24. 24, and then I'd have 27 minus 24. So if I had 6, that would be 6 3/4. So if I had 9 of these that were 3/4, I would only have a length, that would be for a length of board 6 3/4. So right there, that can't be it. We're done. We're done. It's cool, right? But let's try this one. So let's do it a bunch of ways. Let's go ahead and do 11. What if it was 11 3/4 foot boards? That'd be, now I don't know if I showed this, but when you multiply, this is going back to 5th grade. This is just, you can think of this as 11 over 1. So you multiply the numerator, that's 33 over 4. Okay, 33 over 4. You can think, oh, wait a minute, what times 4 is close to 33? Well, how about 8? 8 is 32. 32 1/4. So you could make 11 3/4 boards, and you'd only use up 8 1/4. And how much do you have up here altogether? You have, oh, that's all you have. So he could actually make 11. He could make 11. We just proved our point. That's the answer. Okay, so let me also do this, though. I'm going to show you with some division. So let's do let's work it a different way. Let's think of division here. Division is really fun. So hold on. Let me clear this out. And I would advise you to get a piece of paper and work through this with me on a separate piece of paper. Do all of these different ones. Stop the video. It's good to be able to solve a problem different ways. Okay, so let's do this. Now let's do 8 1/4 divided by 3/4. Okay, so if you can make these are fractions. So if you can make common units is really easy. And these are already in common units, so I can change all of this. You have to be able to change an improper fraction or a mixed number to an improper fraction. So 8 1/4. Well, in each one of these, there's 4 parts in each one of these things, right? So 1, 2, 3, 4. There's 4 fourths in that. So there's 8, and there's 4 parts in each one of those. 8 times 4, that's 32 parts plus this one over here. The other way to think of it is, you say, well, how many parts to make a whole? My denominator shows me there's 4 parts to make a whole. 8 times 4, that's 32 parts to make a whole. So if I make 8 wholes, that's 32 parts. Plus, I've got this 1 in the numerator, shows me I got 1 extra. So let's come up here. So that's 33/4. Okay? Divided by 3/4. Now, because these are common units, you don't have to do anything else. You're with a common unit, so you can just go 33 divided by 3 equals 11. 4 divided by 4 equals 1, which is just 11. Okay? So you may have also learned, this is where you can see I can really save time right there, because if not, if you just say, oh, it's division, so I have to do keep, change, flip no matter what, then you're going to end up with something like this. You're going to end up flipping the second one, and there's actually a quicker way to do that, but I guess I'll just go through this quickly. Then you'd have to end up multiplying this out, so 33 times 4, so now you're getting up to quite a bit. So that's 120 plus another 12, so 132 divided by 12, okay? And then you could do this division, but you could sort of recognize this, and maybe this is a fact, okay? So 12 times 11 would be 132, so you could do it that way. Finally, one more way. You could actually save some time here, because 33, this could become, you could put both numerators together, 33 times 4, and then 4 times 3. It's the same thing, okay? It's the same thing. So and this is something they do show you in Common Core. You put your numerators together because you're going to multiply them and divide by 4 times 3. You can do that because that's all you're doing right here. You're doing 33 times 4 and 4 times 3. And once you've got them in this form, then you can say, you know what, I'm going to divide them anyways, so I could just divide them ahead of time. You can move ahead and divide them. So this I can divide. 4 divided by 4. 4 divided by 4 is just 1. Okay? And 33 divided by 3 is just 11. So you could save some time that way. You don't have to multiply, in that case, everything out. Okay, cool beans. I'm going to save this, and then I'll come back and finish some more on the next video. Thank you.